Hello everybody, please subscribe if you are not subscribed yet, because every day I'm publishing about one or two very good difficult problems in physics and maybe 3 or 4 light problems. So first, today we do this problem, mechanics, weighting the plate. A white plate of width L is lowered vertically into a white container with the water so that its end touches the surface of the liquid. The plate is wetted with the water. The contact angle is theta. Surface tension coefficient sigma. Density of water rho. First question. Find the force of interaction between the plate and the water. Second question. To what height h will the liquid rise at the very surface of the plate relative to the water level in the container? And question 3. Obtain an equation y as a function of x relating the height y of water rise at a point x away from the plate. Solution. First problem is a pretty easy one. So to find what is the force of interaction between plate and water, we have to find what is force F acting on this plate, and we know that this force equal to coefficient sigma multiplied by a length of this line, which is L, and we just need to multiply it by cosine of this angle theta to find the vertical projection of this force. And because we have two surfaces, we have two forces. So the final answer will be total force equal 2 sigma L multiplied by cosine theta. Second question. To what height h will the liquid rise at the very surface of the plate relative to the water level in the container? So we need to find what is this height h. For that we have to investigate the static forces on each part of this water, and let's do this. So we have this picture. Let's take a small part of this water with dx and find out which force is acting on this part of water. We have surface tension from the left, which is going this way, surface tension from the right, which is going this way, and we have force of gravity, which is going down. And the projections of these forces on vertical direction must be equalized, because it's a static position. Let's write equation. Suppose that phi it's an angle between this straight line tangent to our curve, and in this point that will be angle phi plus delta phi. So we can write this static equation that these projections of these two forces, they equalized by force of gravity. So here we have difference between sine phi plus delta phi minus sine phi. We can present force F as a sigma multiplied by L. Let's present this equation in better form. We can divide both parts by d phi, and in that case we have this relation. So our L is cancelled, and we have this part divided by d phi, and we move dx over d phi to the left, and we have d phi over dx. This is our relation. So this part, that's just cosine phi, and we have to investigate what is d phi over dx. So we need to describe it in terms of y and x, and we can do this because we know what is tangent phi. That's the first derivative from y over dx, so we can write it. This is our dependency of phi through y and x, and to get this d phi over dx, we can make first derivative from this expression by dx, so that will be this one. We have a derivative from tangent by phi, that will be 1 over cosine square phi, and we need to multiply it by d phi over dx. And from right part we have a second derivative from y. This is how we can express a d phi over dx, and let's do this. This is our expression, d phi over dx, that's equal second derivative from y over x multiplied by cosine square phi. And now we can put this expression here, and also we have here is cosine phi. So finally from this formula we can get formula like this. And now we can represent cosine phi through tangent phi. Tangent phi, we need to use this formula. So for cosine phi we have this expression. We have cosine phi equal 1 over root from 1 plus tangent phi square, and tangent phi equal dy over dx, and finally we have this expression for cosine phi, and we can put it here in this formula to get completely y-x dependency. Now we have this formula, this equation, and we can try to solve it. So here we can use a standard trick. We can multiply both parts by y prime, which is first derivative from y over x, to make a full derivative from both parts, left and right. Let's do this. This is our equation, and now we can do integral from both parts, and the result will be like this. This is the result of our integration, and here we have a constant c, which we can find from knowledge that when we are very far from y-axis, so we have we have a first derivative going to 0 and the y going to 0. It means that the constant c equal to sigma over 2 rho g, and we can rewrite this equation. This is our result, and now we can find what is the height of this water just near this plate, because we know what is first derivative from y here. That will be tangent phi, and 1 over this square root from 1 plus tangent square phi, that will be just a cosine phi. But phi plus theta, that's a pi over 2, It means that instead of cosine phi, we can write here sine theta. And we have this expression. So we have rho g h square equals sigma multiplied by 1 minus sine theta. Or we can move rg to the right and make a square root, which will give us the answer. So that will be our answer for the second question. But to answer for the second question, we don't need to do integrals. We can do this using just simple Newton law applied to our water above the zero level. Let's check this picture. On this picture I show all forces applied to this part of water above the zero level, and we have surface tension F going on the angle theta to the left. We have force F2, that's a surface tension, to the right. We have pressure from atmosphere, and part of this pressure is going to the left. And we have a force from our plate, which is going to the right. So now we can write the equation for static for these four forces and find what is the answer for our question 2. Let's write it down. This is our equation. Force F1, that's sigma L multiplied by sine theta, that's a horizontal part of this force applying to the left. Also we have force from atmosphere, which is if we project it to the left, we have to multiply pressure by area, which is H multiplied by L, and totally that's a PHL. So these are two forces acting to the left, and they must be equalized by forces acting to the right, which is force of surface tension going straight horizontally, that's sigma L, plus force from this plate. We can count this force next way. On the zero level we have pressure equal atmosphere pressure, but when we're going up, this pressure is decreasing linearly. So we can subtract this average linear force using this this expression. And now that will be our total force from this plate. If we look at this formula, PHL is cancelled, L is cancelled, and we can rewrite this equation in form of, and again from this equation we can write what is the H. Again we have the same result as in this straight previous way. And last question. Obtain an equation y as a function of x relating the height y of water rise at the point x away from the plate. So we need to solve this equation, and we can split variables and we will get this result. And now we can integrate both parts, and for that we have to make a substitution. Substitution will look like this, and after that we can put this instead of y and do integral. This is our integral, which is a table integral, and now we have this result, and we can do backward substitution, which give us this expression. To find what is a constant c, we can use this knowledge that for x equals 0, y equal h in the previous counting. From that point we can find that c equal this expression. So that's our solution. We have x as a function of y, so that's a reverse function, which is solution 2. That's it. This is the answer for question 3.